This video is about cleaning up some of the leftover issues with elimination reactions, and if there's one core issue I want to bring up here, it's that E2 eliminations are fast and directly analogous to SN2 type reactions. In other words, a collision is the main thing that happens, and basically if you have a base and elimination reaction is going to happen, then E2 is what's going to happen first. The presence of a base speeds up an elimination reaction, whereas E1 eliminations are always slow, and that is because first the substrate has to decompose, and then essentially the carbocation needs to sit around and not react with any nucleophiles that are present, and instead something will deprotonate it and lead on to the product. So in other words, if you have a base present, E2 elimination is going to happen relatively quickly and it's going to predominate. E1 eliminations often happen under acidic conditions with no base at all. Although you could have E1 eliminations under some circumstances with a base present, but they are relatively unusual circumstances. So again, E1 reactions are slow, the material has to decompose, and then there's no nucleophile around good enough to attack the carbocation, and basically the E1 happens by default. Whereas E2 reactions tend to be fast. And E2 reactions are often fast enough to be competitive with everything else, or even happen faster than everything else. So keep that in mind. E2 eliminations are quick collisions between a base that's strong enough to do a deprotonation. E1 eliminations are the material decomposes, it sits around for some lifetime, nothing else really happens to it, and eventually it decomposes onto the double bond. And that central fact that E1 eliminations are relatively slow is in fact what ends up driving a lot of the chemistry, and of course is the source of the competing images that you might get from the Pelkey handout, which talks about how Zaitsev is the major product because it's under thermodynamic control, and the Miller handout, which talks about how they're relatively unselective. And as I mentioned, both of those thoughts are true. It's just you need to keep in mind you're going to favor the thermodynamic product while also making everything else. And so if you have a reaction set up like this one, again, under acidic conditions, so there's no base at all, which is going to make this a relatively slow reaction, will lead to multiple products, and it will tend to favor the Zaitsev product as the major. So let's start by drawing out a good Lewis structure for the acid. The OH is not yet a leaving group, but in the presence of acid, it will become a better leaving group. pKa at the moment is 16. This now generates the protonated alcohol, and this is a terrible leaving group. This is now at least a plausible leaving group, so it leaves on its own. pKa now is -2, which is in the appropriate range. The water that just left is floating around nearby and will likely serve as the base for this process, or alternatively can recombine and go back the way you came. There are multiple different pathways that this reaction could take at this point, but deprotonation at this stage will lead to the hot Hofmann product. If instead the water can deprotonate at this position, what it will likely do is form the internal double bond, which would be the Zaitsev product, and particularly it will favor the trans internal double bond as the Zaitsev product. Of course, it's not out of the question that you will make some cis Zaitsev product at this stage, although it will prefer the trans because the trans is the more stable. And of course, the last thing to keep in mind here is that this material can undergo a hydride shift to lead to a more stable secondary carbocation. Right now we have a secondary carbocation, but if that hydride shifts over, then you have a secondary carbocation that's also stabilized by resonance. With this cation now being stabilized by resonance, and of course, the water can come in and deprotonate at this stage, again, preferentially leading to the trans Zaitsev product, but also possibly leading to the cis material as well. And so once again, the key thing to recognize is that this is a relatively slow process where first you protonate, this then leaves, you now have a carbocation. This carbocation will hang out for some lifetime. You can even do a rearrangement to the more stable secondary plus resonance carbocation, which can then be deprotonated. Once you have made it to the secondary carbocation, you will lead to the Zaitsev internal double bond products, favoring the thermodynamic one for sure. Definitely going to have more of the trans than you will of the cis, because again, this is under thermodynamic control. In other words, you're going to try to access the lowest possible energy state. So this isn't happening quickly, this is happening slowly, and it's sampling all possible outcomes. But even if the water comes in and deprotonates originally, which leads to the Hofmann product, there's going to be at least a mixture of products formed. So at the very least, what you will have is all three of these products. And so Prof. Pelkey's handout is correct. You're going to be favoring the most stable one, and this is not a process that happens quickly. But Prof. Miller is also correct in that there are many, many possible products, and you will almost certainly make at least some of all of them, while perhaps favoring as the major, the most stable product. And the last thing I want to discuss here, I want to discuss largely because it's so unusual, that nitrogen doesn't usually act as a leaving group, even though in this particular case, as a cationic nitrogen, it can leave as the neutral species. And so you could imagine drawing an arrow where it just plain leaves, but that's not the way this reaction goes. This is an unlikely leaving group, even though it's leaving as a neutral. It can, however, be kicked out in the presence of excess sodium hydroxide, so a lot of sodium hydroxide, especially if you're heating up this mixture. And in this case, there's two potential outcomes. One is that you do sort of an E2 elimination here on the external hydrogen, and that will lead to the Hofmann product, which will be preferentially formed. Here, you could also, of course, abstract this hydrogen and lead to the tri-substituted Zaitsev product, but in fact, you're going to form the Hofmann product as the major when you have nitrogen as the leaving group. And the reason for that's a little odd, but you might look at this and say, oh, well, these are relatively similar and this is a tiny base and so on, but what you're not keeping in mind is that the nitrogen actually has 3 different metals on it. So this group right here is huge, which means that it's actually congested to try to get in there, even if your base is small. And so here you're going to have a strong preference for abstracting the hydrogens that are more accessible just because of how big the leaving group is. And so that's the predominant reason why you're going to form mainly the Hofmann products. It's easier to get at these, and even though this is a small base, it's really hard to get at the one that will lead to the more stable product. So if the quaternary amine is serving as a leaving group, then you're going to predominantly favor the Hofmann product for kinetic reasons. Even with a small base, you can access these hydrogens in a way that that one's just challenging to get to. So keep in mind that E1 eliminations tend to happen slowly. When they do happen slowly, often what that means is that you're under thermodynamic control, but there's going to be at least some preference for removing the charge along the way by just reacting with whatever's nearby. So even though they're under thermodynamic control, they're not particularly selective.